So in this lecture I will discuss about measurability. So let me give you a typical example of the assertions we will prove. I will consider always a measurable space, a function f, which takes value in the extended line. So maybe two functions of this type, and I will assume that they are measurable. And I will try to prove that the product, say, it's measurable. Right. Or if I take a sequence of functions which increase, each element of this sequence being measurable, I want to show that the limit is measurable, and this type of assertions, right? So let me state a lemma. Our first result. So I'm assuming that I have G and F, which are extended. G and F are measurable functions. And then I have also, let's say, alpha, which is a real number. So I want to prove that alpha times f is a measurable function. So instead of writing it's a measurable function, I would say that it belongs to f. So this means that alpha f, it's a measurable function with respect to the sigma algebra f. Right, then I want to say that alpha plus f is also a measurable function. Then maybe we want to prove that f plus g, it's a measurable function, that f squared, it's a measurable function, that 1 over f is a measurable function, and f plus, f minus, and modulus of f are measurable functions. Right? And then we'll prove that f times g is also a measurable function. Right? So we are assuming that g and f are measurable functions, that alpha is a real number, and we are proving that some algebraic operations with these functions are still measurable functions. So let us prove this lemma. So the first claim is that alpha f is a measurable function. Okay? So we have seen that in order to show that alpha f is a measurable function, I have to prove that the inverse image by alpha f of any set of the form which is an interval minus infinity x, it's measurable. So we have to prove that the sets of omega for which alpha f of omega is less or equal than x, that this set belongs to f, knowing that f is measurable. Okay, so, well, here, let's assume, well, if alpha is equal to 0, there is nothing to prove, because then alpha f is equal to 0, and here we have a constant function, and the constant function, it's a simple function which is measurable. So there is nothing to prove. If alpha it's bigger than 0, then alpha f omega to be less or equal than x, it's the same thing as f alpha to be less or equal than x divided by alpha, and we know that the set of omegas such that f of omega is less or equal than x divided by alpha, that this belongs to f for all x, because f it's measurable, right? So if alpha is positive, it's clear that alpha f is measurable. Now if alpha it's negative, then, well, the set for which alpha f of omega is less or equal than x coincides with the set of omegas such that f of omega is greater or equal to x divided by alpha. And again, we have seen that the set of omegas for which this inequality holds belongs to the sigma algebra f, because f is measurable, and therefore if alpha is negative, we have again that the function alpha f is measurable. So in this case, as you can see, the proof is very simple. So now let's prove B and C. I want to show that f plus g is measurable if both f and g are measurable. So to prove that f and g is measurable, we have to check that the set of omegas in omega, for which f of omega plus g of omega, it's say smaller than a, that this set belongs to f. And since I'm using x, let me replace that by x, and I have to show that this holds for any x in R. Well, but what I claim is that if two numbers, the sum of two numbers, is smaller than x, then there exists a rational number. So there exists a rational number such that f of omega it's smaller than r, and g of omega it's smaller than x minus r. Right? So, well, on one direction it's clear if f of omega is smaller than r and g of omega is smaller than x minus r, then the sum of f of omega and g of omega is smaller than x. This is clear. But also, if I have sum of two numbers, we can always find a rational for which f of omega is smaller than r and g of omega is smaller than x minus r. I leave the details to you. And in this case, well, we know once we have this identity, since f is measurable for any r rational, this set belongs to the sigma algebra f. The same claim holds for this set because G is measurable. Now, the intersection of two sets in the sigma algebra f belongs to the sigma algebra f, and since we have here a countable union of elements in f is an element in f, so this proves that for any x in R, this set belongs to the sigma algebra f, which proves that f plus g is measurable. So now let's prove D, which is that f squared is measurable. So in order to prove that the function f squared is measurable, we have to check that the set omega such that f omega square smaller than x belongs to f for any x. So it's clear that if I take first a real number x which is less than or equal to 0, then there are no omega for which f omega squared is smaller than x. Therefore, this set is empty, and the empty set belongs to the sigma algebra F, so there is nothing to prove in the case in which x is less than or equal to 0. Now let's assume that x it's strictly bigger than 0, and so we are looking for the points omega for which f omega squared is smaller than x. So this set coincides with the sets of points omega such that minus x is smaller than f of omega, which is smaller than x. And since f is measurable, this set is just the inverse image of the interval minus x, open interval minus xx, which, since the open interval it's an element of the Borel, extended Borel sigma algebra, this set belongs to the sigma algebra F because F is measurable, and therefore this set for any x in R belongs to the sigma algebra F, which proves that F square is measurable. From this result, we can immediately obtain that the product of two measurable functions f and g is measurable, because I can always write fg as 1/2 of, say, f plus g square minus f square minus g square. Right? So we have seen that the sum of two measurable functions is measurable, that the square of a measurable function is measurable. So all these terms here are measurable. We've seen that if we multiply a measurable function by a real number, it's a measurable function, and that the sum of two measurable functions is a measurable function. So this proves that fg is a measurable function. So now let's go to the proof that 1 over f is a measurable function. And again, we have to show that the points omega for which 1 omega in omega, for which 1 over f of omega is smaller than x, that this set belongs to the sigma algebra F for any set x, any point real number x. So for that, let me draw here the graph of the function 1 over x, or 1 over z. So here's the graph of the function 1 over z. And so I will define that in several cases. The first case, let's assume that x is strictly positive. So I want to identify the points in this graph of the points in which 1 over z, it's, so let me call that function h, it's smaller than x. So here is the point x, and I want all points z such that 1 over z it's smaller than x. So you see that you have all the points between minus infinity up to 0. I didn't say, but here I'm assuming that 1 over 0 will be equal to plus infinity. So the point 0 it's excluded. And then we have, well, this point here it's x, so the point here it's 1 over x, and we have the interval 1 over x plus infinity. So in the case in which x is positive, the sets of omega such that 1 over f is smaller than x corresponds to the points omega for which either f of omega is strictly smaller than 0, or f of omega is strictly bigger than 1 over x. One over x. Right? So I just rewrote 1 over this set as the union of these two sets, which you can check or you can verify by looking at this graph. Since f is measurable, this set and this set belong to the sigma algebra F, and therefore the union belong to the sigma algebra F. So the case in which x is strictly bigger than 0 has just been checked. Now let's look at x equal to 0. So we are asking what are the points for which 1 over f is smaller than 0. Well, this is exactly the points in this case of all omegas for which f of omega is smaller than 0. Right? So you can again check that in this graph. If you take x equal to 0 and you look at all points z for which h of z is smaller than 0, you get the interval minus infinity up to 0, which means all points omega for which f of omega is smaller than 0, and this is again an element of the sigma algebra F. Finally, if you take a point x which is smaller than 0, let me erase this piece of the graph. So here is the function h z, which is equal to 1 over z. Let's fix a point x which is negative, and then let's observe the points z such that 1 over z it's smaller than x. So you see the points for which z, which 1 over z is smaller than x, this point here it's 1 over x, here is 0. So these are all points which are between 1 over x and 0. So this corresponds to all omegas such that 1 over x is smaller than f of omega, which is smaller than 0. And well, and again, since f is measurable, this set belongs to the sigma algebra F. And therefore, we've proved that in all three cases, the inverse image of minus infinity x belongs to the sigma algebra F, which proves that 1 over f it's a measurable function. Now, to complete the proof of the lemma, it remains to show that the positive part, the negative part, and the absolute value of a function, measurable function, f is measurable. So let's see, let's consider f plus, which, remember, it's the maximum of f and 0, and we have to investigate the sets omegas such that f plus of omega it's smaller than x. Right? So if x it's less than or equal to 0, so f plus is the maximum of f and 0, which means that f plus it's always greater or equal than 0. Therefore, this set it's empty if x it's less than or equal to 0. While if x it's positive, then this set, so I need the maximum between f and 0 to be smaller than x, but 0 it's always smaller than x because x is positive. Therefore, this set corresponds to the set of omegas such that f of omega it's smaller than x, which is an element of the sigma algebra F. So this proves that f plus, the non-negative part of a function f, is measurable whenever f it's measurable. F minus, remember, it's equal to the maximum of minus f and 0. So again, f it's measurable, so minus f it's measurable, and we have seen that the maximum between a measurable function and 0 is measurable. so f minus is measurable. And now f, the absolute value of f, which is the sum of f plus and f minus, it's also measurable because we proved that f plus and f minus are measurable. So this completes the proof of the lemma. Now let's prove a lemma. On sequence of functions. So I'll take a sequence fn of functions. So these functions are defined on a common space omega. They take value in R bar, and they are all measurable. So I want to prove that the supremum of these functions is measurable, and therefore the infimum then I want to prove that the limit sup, which is always well defined of these functions, is measurable, the limit inf, and when I'm speaking about sup, lim sup, I'm always talking about pointwise convergence. Right? So this sup is defined point by point. I'm taking the sup of fnx, of fn omega for each omega. And finally, if the sequence fn converge to some function f pointwise, I want to show that f is measurable. So this shows that the measurability is inherited by sups, lim sups, and by limits. The proof of this lemma, it's very simple. So let's first prove that the supremum of fn is measurable. Well, so let's consider the set of omegas such that the supremum over n of fn omega, it's greater than a. Well, to say that the supremum it's greater than a, or let's use x. So let's fix x in R, a real number. Well, I claim that this is exactly the union of the omegas such that fn of omega is bigger than x. Right? So if the supremum it's larger than x, then there should be 1 which is larger than x. Otherwise it will be less than or equal to x, which is exactly what's stated in the right-hand side. So all these sets are in the sigma algebra F because we assume that Fn it's measurable, and therefore the union is in the sigma algebra F, which proves that the supremum it's indeed measurable. Now once we know that the supremum is measurable, we can deduce that the infimum it's measurable because we can always write the infimum as minus the infimum. Minus the infimum is the supremum of minus Fn. Right, so Fn is measurable. We've seen that minus Fn therefore is measurable. We just proved that the supremum is measurable, and therefore minus the supremum is measurable, which shows that the infimum is measurable. So once we know that, we can go to the limit sup of Fn. Well, but the limit sup can be written as you take the supremum for n greater or equal than k of Fn. So by the first part of the proof, for each fixed k, this supremum it's a measurable function. Now if I take the infimum over k, I obtain the limit sup of fn, and we have seen that, by the first part of the proof, that the inf of a sequence of measurable functions is measurable. So this object is measurable, and we can apply the same argument to the limit inf, or again play with minus sign, putting minus minus, and introducing the minus inside to transform a lim inf in a limit sup. So the same argument applies to lim inf of fn. And finally c, well, if we have a sequence fn converging to f pointwise, this means that f is equal to the limit sup of fn, because fn is converging to f, and by the previous part we obtain that f is measurable, which completes the proof of this elementary lemma. So let me just make a comment here. We are taking supremums or infimum in this lemma over countable sets. A similar statement will not be true if we don't take countable sets. Let me give you an example. So we have seen, let's take the interval or the line. Let's take the set R with the Lebesgue sigma algebra and the Lebesgue measure. We have seen that there exist, in the first lecture I proved that there are sets which are not Lebesgue measurable. Right. So let me consider A a set which does not belong to the Lebesgue measurable. It's clear that A is not countable because all countable sets belong to the sigma algebra of Lebesgue. Now let's take a function. Let me call ft for t in R. The function ft, which is defined on R to R, and which take the value 1 at t and 0 elsewhere. So ft is the indicator of the point t. So ft of x, it's equal to either 1 if x is equal to t, or 0 if x is different from t. So ft it's a simple function for each t, and therefore it's measurable. But now if I consider the supremum over t in A of ft, I get the indicator function of the set A. And the indicator function of the set A, it's clearly not measurable because the inverse image of 1, it's A, and A is not measurable. So you see that when you take uncountable supremums over uncountable sets, there is no guarantee that the object you obtain, the function you obtain, it's measurable. And this will be a problem, for instance, when studying stochastic process. You have a process which is indexed by time, so you take very often a supremum, say for t less than t, of your stochastic process ft, and you want, of course, this function to be measurable, but you're taking here a supremum over an uncountable set. So in order to show that this function it's measurable, you will have to show that you are allowed to replace this supremum over an uncountable set by a supremum over a countable set. And for this replacement, you'll need nice properties of your process. For instance, if the process is right continuous, you can always replace this supremum by a supremum over a countable set. But in general, in order to perform this replacement, you will need to prove regularity properties of your stochastic process. So it's important to keep in mind that when you take supremum, infimum, and operations over uncountable sets, you might find problems. So up to this point, we never used any specific property of the set omega. So now let's assume that omega is a topological space. And that we have a sigma algebra F, which contains the Borel sigma algebra. So that we have a space, a measure space, and let's say that we have a measure mu. And we have a function f, which is defined on omega, and take values on the extended real line. So my observation is that if f is a continuous function, then it's measurable. And well, this is clear because we have seen that to show that a function is measurable, it's enough to prove that the inverse image of intervals of the type minus infinity a, for a real number, it's enough to show that this set belongs to the sigma algebra F for any a. Well, but this set, it's an open set. Since f is a continuous function, it brings open sets into open sets. So the inverse image of this open set, it's an open set. Being an open set, it belongs to the Borel sigma algebra. And since we are assuming that the sigma algebra F contains the Borel sigma algebra B, this set indeed belongs to F, and therefore the function f is measurable. So when you have a function which is defined in topological space which is continuous, it is also measurable. So this is a very simple observation. Another simple observation is that the measurability of a function defined on omega depends on the sigma algebra. Correct? We are requiring that the inverse image of any set A in the extended Borel sigma algebra belongs to the sigma algebra F. So it might be possible that you have in this set omega several different sigma algebras defined. You can, for instance, as an example, you can think that omega is the real line, and we have seen that in the real line there are at least two different sigma algebras, the sigma algebra generated by the open sets and the one which is obtained by completing this sigma algebra with respect to the Lebesgue measure, which we are representing by L and calling the Lebesgue sigma algebra. So maybe in this space omega there are many different sigma algebras, and it's clear that if you have a sigma algebra F which is contained in a sigma algebra G, and if a function f it's measurable with respect to the sigma algebra F, it will be measurable with respect to the sigma algebra G, right? Because, well, to show that it's measurable with respect to G, we have to prove that the inverse image of a set A in the extended Borel sigma algebra belongs to G, but it's F measurable, therefore it belongs to F, and F is contained in G. So this remark just to stress the fact that when we speak about measurability, there is always behind a sigma algebra, and maybe there are many sigma algebras defined in omega, so you have to specify to which sigma algebra you are referring when you say that a function is measurable. So to conclude this lecture, let me speak about properties which hold almost surely. So again, fix a measurable space omega f and mu, And let's consider a property P. So P, it's a property. To fix ideas, you can imagine that there is a function f, which is defined on omega and taking values in the extended line. And the property can be, well, all the points omega in omega, such that f of omega is equal to 0. So a property means a subset of omega. So we will say that a property P holds almost surely, sometimes also almost everywhere, if we can find if there exists a set E which belongs to the sigma algebra F, and such that mu of the complement of E is equal to 0, and the property P holds on the set E. So in our example, we will say that f is equal to 0 almost surely, well, if you can find a set E in the sigma algebra, because we are giving a measure to the complement of E, so that if there exists a set E in the sigma algebra, such that the complement of E has measure 0, and such that f of omega is equal to 0 for all omega in E. So this is a property, this is what we mean when we say that some property holds almost everywhere or almost surely. And here is an important observation which explains why the Lebesgue measure has some properties which are completely different from the Borel sigma algebra. So let's consider the real line R, and let's represent the real by B the Borel sigma algebra, and by L the Lebesgue sigma algebra on R, and let lambda be the Lebesgue measure. Now let's assume that we have a function f, which is defined on R and taking value on the extended line, R bar. And let's assume that this function is L measurable. So that it is measurable with respect to the sigma algebra L. So here, as I mentioned before, we have two sigma algebra. Therefore, when speaking about measurability, I have to specify to which sigma algebra I'm referring. And now let's assume that we have a function g, which is also defined on R, taking values on R bar. And let's assume that g is equal to f almost surely. Then I claim that G is also L measurable. And you'll see that it will be very important in order to prove that assertion, that statement, that the sigma algebra L is complete with respect to the measure, the Lebesgue measure. So I want to show that G is measurable, and therefore I fix a set A in the extended Borel sigma algebra B bar, and I want to prove that the inverse image of A belongs to L. Right? This is what I need to show in order to prove that G is L measurable. So let's write this set. This set is the set of omegas in omega such that G of omega belongs to A. Well, I want to show that this set belongs to L. So since G is equal to F almost surely, by definition, there exists a set E in the sigma algebra L, such that mu of E complement, L of E complement, it's equal to 0, and F of omega, it's equal to G of omega if omega belongs to E. So I will rewrite this set by taking its intersection with E and E complement. So this set will be equal to the omegas such that G of omega belongs to A, intersection E, union the omegas in omega such that G of omega belongs to A, intersection A complement. Well, on the one hand, since F is equal to G on E, on this set I can replace G by F. And after replacing G by F, this is the inverse image of A by F, which belongs to the sigma algebra L, because I'm assuming that F is L measurable, and E also is L measurable, so this first set belongs to L. On the other hand, this second set, it's contained in E complement, which is an element of the sigma algebra L, and which has measure 0. So this second set is a negligible set in the sense that it's contained in a set which has which belongs to the sigma algebra and which has measure 0. Since the sigma algebra L is complete, this set also belongs to L. And therefore, we proved that the inverse image of A by G is an element of the sigma algebra L, and therefore is G is L measurable. So you see, we used here strongly the fact that L was complete in this proof. So the same statement does not hold for the Borel sigma algebra. And we will be using this fact several times. So we will need to show that some functions are measurable. The only property we know is that they are equal to some other function which is measurable. They are equal almost surely. And therefore, we'll be forced to use the Lebesgue sigma algebra in order to guarantee that the function is measurable and not the Borel sigma algebra. So this will explain why in many situations we will be using the Lebesgue sigma algebra instead of the Borel sigma algebra. One final comment in these lectures, compositions. So let's assume that we are working on some space omega with a sigma algebra F and a measure mu. And so that we have a function F from omega to R, which is measurable with respect to the sigma algebra. And there is also a function G, which is defined from R to R. And so it will be measurable by considering here the sigma algebra generated by the Borel, the open sets, the Borel sigma algebra. So I'm assuming that the inverse image of any set B belongs to the Borel, well, let's say the extended Borel sigma algebra, if for any B which belongs to the extended Borel sigma algebra. Right, so I'm assuming that there exists a function G which is measurable if in the starting set we consider the extended Borel sigma algebra. And my claim is that, well, now once you have a function from F from omega to R, and the function g from R to R, you can take the composition of these two functions. So define g composed to f, which is a function from omega to R. And my claim is that this function, this composition, is, well, f measurable. Well, and this is very easy to prove that this function is f measurable. Fix a set A in the extended Borel sigma algebra. We have to show that the inverse image of this set by the composition G with F belongs to F. But the composition, the inverse image of the composition, it's the inverse image by F of the inverse image by G of A. Since G is measurable with respect to the extended Borel sigma algebra, G minus 1A belongs to the extended Borel sigma algebra. So this is the assumption on G. And since F is measurable, if you take a set which is in the extended Borel sigma algebra, its inverse image by F belongs to F. So this proves that this set indeed belongs to F, and therefore that the composition is F measurable. So this will be used also many times. For instance, this proves that if you have a function, the square of the function is measurable because we can consider that you're taking the composition of f with the function g, which associate to x squared. This function is continuous, so we've seen that it's measurable, and therefore by applying this result you obtain that f squared is measurable, a property which we proved in the previous lecture, but that would give you an alternative proof. So with that, we conclude this lecture.